Hello everyone, welcome back. It's been a while. It's been a busy week for me, right? So I try to pause as many video as I can from this point onward. Right now, today I try to walk through questions related to three-dimensional vector. Right? Okay, let's go through this. Okay, now we have a line L given as or given by this vector equation where lambda is a scalar parameter and the plane equation pi has an equations given by r dot. This is the scalar product with I j minus 2k equal to 19 there. So our first question is to find the coordinates of the point of intersections between the line L and the plane pi here, right? Okay, now let's look at how to work this out, right? Now, generally, here I'm just going to draw a rough sketch. So, take for instance, you have a plane here. So, this is a plane. Okay, this is plane pi, for instance. And then we have a line. Okay, so the line could be something like this. Okay, so this is line L here. And then line L intersect with this plane pi at this point. Okay, now why don't let's call this point as point P then, for instance. All right. So our intention is to find out. Um, of course, the first thing you like to find out is whether the line L and the plane does meet at the point or not. If they do, then yes, we will get a unique solutions for the lambda here, right? Now, the strategy that we're going to use will be here. First of all, because the point P is located on the line L here, so therefore we can describe this equation of line in a more compact form. So originally, okay, maybe I'm going to write it down in a vector, column vector form, which I'm more comfortable with. Okay, this is what I have. Okay, now there you have it. We can also write this in a more compact form. For instance, -2 plus lambda. Okay. Now this generally shows any points on the line, knowing the unique value or values for lambda here. Okay. And now we can also um, label. In this case, I can say that because P is on the line L, so therefore it's possible that P can be represented by this general point given by this. Right? Now, if you are able to find a unique value for lambda, therefore, we will be able to find the exact position vector for P here. Okay, and then for the plane pi, this is a vector form of the equation for the plane. Now, we are going to convert this vector form into a Cartesian form. Okay, now from here, this is vector form. Oops, let me get that correct. Okay, that is actually equal to 19. Now we can actually convert this into a Cartesian form, right? Now we know that R can be represented as x, y, z in this case. Okay, now therefore, these plane equations can be written as x because it's a um, scalar product. So therefore, we can write xy minus 2z equal to 19 here. All we need to do is multiply each elements and then obtain the sum of all the products of their elements. And then that will be our plane equation. So this is our plane equations pi in a Cartesian form, right? And then OP has this general uh, position vectors here. And then we know that each row here actually represent x. Okay, this one generally can be represented as x, y, z like this. Okay, and then if P does intersect with the plane pi there, therefore this lambda would satisfy this Cartesian um, equation, right? Now, in order for this OP to be intersecting, in order for the P to be found on the plane pi here, which indicate that the line L actually intersect with the plane pi. So we're going to solve these two equations simultaneously. So I'm going to label this as my first equation, and then this one will be my second equation here. So all we need to do is just solve this simultaneously. How do we solve it? All we need to do is just substitute the x component here into the x here, the y into y. All right, now therefore, so from here, we will have 2 plus 3 lambda, and then plus y, which is 1 plus 2 lambda, and then minus 2z. Okay, so 2z will be 2 negative 2 plus lambda, and then that would be equal to a 19. Okay, so I hope that is clear. And then from here, we just need to solve this. Okay, so let's see what do we have here. We have a negative 2. Okay, so therefore we only have lambda, 3 lambda, and then we have 3 here, and then that will be a 7, 19, sorry. Let me check whether that is correct. 3, 4, 3, 4, 7. Yes, correct, right? So therefore 3 lambda will be equal to a 12, and then therefore lambda is a 4 there, right? Now we do get a unique value for lambda. Therefore, therefore L, the line L does intersect with the plane at point P there. Uh, then finally, we're going to summarize the position vectors for P in this case by substitute lambda equal to 4 into equations number 1. Therefore, position vector OP is given by 14, okay, 9, and then a 2 here. All right, now I hope that is clear. How do we obtain the point or intersections between a line and a plane in three-dimensional space using vector methods? In this case, we are applying the scalar products methods. All right, now I hope that is clear for first questions there. All right, now stay tuned for the next one shortly. All right, question 2 here. We are still referring to the same object in three-dimensional space. We have the plane, and then we have the line here, right? So for this second question, the perpendicular to the plane pi from the point 2, 1, negative 2 meets pi, the plane, at the point B here. So we need to verify that the coordinates or the position vector is given by 4, 3, negative 6. Okay, now let me indicate that where is this point located, right? So we know that A, you can see that position vector A, 2, 1, negative 2, is actually found on the line here. So this is actually A. Okay, and then the perpendicular line to plane pi from A meet at the plane pi at point B. All right. So we have a okay, we have a line sort of. So the line meet with this plane perpendicularly at this point here, B. Right. Okay. So generally that's how it look like. Okay, you can represent it based on your perspective. That is the perpendicular to pi from the point A that meet the plane at point B. All right, so I hope that is clear. Now we need to verify that the position vector of point B is given as such 4, 3, -6 then. All right. Okay, so how are we going to do this? Now, first of all, we're going to make use of the normal to the plane. So the normal to the plane is given by this. This normal, I'm going to label the normal here. Okay, this normal is given by, okay, I'm going to write that down. Normal is given by 1, 1, -2 here. And then this normal here is parallel to this vector AB or BA in this case. Right? Okay, so in order to verify this position vector B, we are going to form a line equations that passes through point A, and then that is perpendicular to the plane pi here. All right. So all we need to do is the line equation um, parallel, I would say parallel to, okay, shouldn't be parallel, perpendicular, sorry, perpendicular to pi and passes through A is given. Right, so this line equation is given by R. Okay, now because this line equation passes through A, so we can write that down as 2, 1, -2 here. Okay, and then in the same direction as this normal to the plane, which is given by this -2. Okay, and then we're going to apply the same strategy. We can write this in the compact form, so therefore that will be this. All right, and then this actually represent all the points uh, for the line that passes through A, and then in the same direction as the normal. Right? Okay, so from here we can also indirectly we can write that as OB. Okay, OB would also have this general equation, vector equation. Okay, and then since B passes through or intersect the plane, sorry, since the line passes through A, intersect with the plane at B, therefore we are going to solve this equation here simultaneously with the plane equations that we have already located in our previous question, right? So from here, I just like to stress again, this section is X, this is Y, and then this one is a Z here. All we need to do now is just substitute these elements into X, Y, and Z. And then therefore, from here, we will have 2 plus mu plus here. And then finally, we have that -2 go to 19 here. Right. And then by solving this, okay, let me see what we have. 4, 6. Okay, so 6 mu is equal to, let me see, 3, 7. 3, 7 is a 12. Therefore, we have a mu equal to a 2 here. Right. So the unique value for this position can be found when mu is equal to 2 here. Okay. Therefore, we can summarize the position vector for B. Therefore, we can say that position vector B, OB in this case, can be given by, all right, so just substitute the mu 2 into this equation here. We have 4, 3, and then finally we have -6 here. All right, so there you have it. you can see that we have managed to verify the position vector B, or the coordinates for B in this case, right? So I hope that is clear for this question here. Right. Now stay tuned. I'm going to move on to the next one shortly. All right, question C. Okay. Now the point A is reflected in the plane pi to give the image A prime. Sorry, let me clean that up. To give an image A prime. Now the A prime, according to this diagram, the A prime would be somewhere here. That will be our A prime. It's a reflection about the plane pi here. Okay, now that will be our reflection. And then we need to find the coordinates for A here. Okay, now that will be quite direct. We know that from here, now we know that AB, AB, in this case, we know that AB has the same magnitude as BA, and then both of them are also parallel. So therefore, we can say that AB is the same as BA here. Okay, right. And then AB, yes, we can obtain the relative vectors between AB here. So I'm going to work out the AB first. So the relative vectors between AB. Now we know that our position vector for B is given here. So therefore, AB is given by OB, OA. And then that is typically 4, 3 with A. Okay, there's our A here. And then therefore, we will get a 2, 2, and then this is a negative 4. Right. Now that will be our relative vectors for AB in this case. And then we're going to work out the relative vectors for BA here. Now, if we are interested to locate the position vector for A prime here, we can just label this as I'm going to label the position vector for A prime here as just XYZ. It'll be easier to um, match with the value in a while, right? So from here, our BA prime is actually given by XYZ, subtract off with OB. So OB is here. Okay, now that will give us this and Z plus 6 here. Right. And then knowing that this equation is true, therefore we can solve this. We will know that x minus 4 must be equal to a 2. Okay, and then that would mean x is equal to 6. And then next we have y minus 3 is equal to 2 also. Therefore y is equal to 5. And then lastly, we have z plus 6 is equal to negative 4, which imply that the z must be equal to negative 10. Therefore, we can conclude that the position vector OA prime is given by the value for x, 5, and negative 10 here. Okay, so I hope that is clear. All right, so stay tuned. I'm going to move on to the next question. All right, after checking back on the position vector of P, it is given as such 1492, right? So I'm going to use this as a position vector where this line L prime passes through. So that will be OP in this case. And then I might want to use a parameter T, for instance. And then in the directions A prime P, for instance. Okay. So all I need to do is, okay, so I'm going to substitute directly. So from here, my OP is basically just 14, 9, 2. And then A prime P is 14, 9, 2. subtract off with the position vector for A in this case. So that will be 6, 5, negative 10. Okay, so here I will have, right, let me see what do I have here. We have 8, a 4, and then a 12. 4 and a 12. Yep, correct. Right. So that will be the line equations for L prime. Okay. And then we are almost done. It's just that this line equation is in a parametric form. It's still in a vector form, but it is more like in a parametric form. How can we convert this into the vector product form? Okay. Now this is how we're going to do it. And so I'm going to erase off this. Okay. Gonna write down this side. In order to do that, all we need to do is we do a bit of multiplications. So here, I'm going to rewrite this one more time. So there's R equal to 14, 9, 2. Okay, what we are going to do now is we're going to um, perform a vector products both side by this vector here. Okay, and then lastly 8, 4, 12 also cross with 8, 4, 12. Okay, right. And then we know that both of these vectors are parallel to each other. So if we perform um, a vector product, this result will end up with 0. Okay, so therefore we have R, and then this is our cross our vector product. So let me try this out. It's a huge number here. Okay, so there is a 108 minus 8, so 100. And then the next one will be, okay, please forgive me, let me do a bit of manual calculations here. So the second one will be like 14, 12 here, 28, 14. Okay, so minus of a 10. So minus of a 10, there will be 158. Okay, negative 158 here. And then my last number here will be 56. Is it 56? Yeah, 56 minus 72. 72 here. So therefore, my final answer will be like 26. So minus is minus here. Okay, so therefore, this is the vector form of the line equations, but more in a vector product form. Okay, so from here you can see that the A, so we can finalize that. Therefore, A, the vector A in this case, is actually given by 8, 4, 12, whereby B, vector B itself, is given by 100, negative 158, and negative 26 here. Right, okay. So there you go. How do we actually convert um, a line equations in a parametric form into a line equations in a vector product form? Okay, so I hope that has been a useful information or learning details for you guys. All right, stay tuned until I upload more videos in the futures. As usual, if you like what you are looking at, do subscribe and then press on the notification bell so that you can receive the latest video. All right, until I see you guys again, take care, everyone.